Just my saying the word printf should cause you physical pain. Certainly haven't been through it enough. So normally about this time, whenever I give Lab 2, I get multiple people pounding me in my office saying, I don't understand a thing. So either Lois is doing a fantastic job of helping you guys with your questions. You guys are the best group that I've ever had. Or there's some acknowledgement of the fact there might be other classes. There's a lot of classes. There is strategy to that.
What's your real office?
My real office location shall be unknown. It's actually in my basement. So, I'm happy to meet with you if you're stuck. I really do enjoy hanging out with students, and it seems that I've done not very much of that this semester. So if you're stuck, please do come and talk to me. If my office hours aren't convenient, let me know. I will meet with you at a different time. Okay? So I am happy to be used as a resource to help you guys get through these labs. I know that I can give you tough stuff to do, and I want to help. So yeah.
What's your day like tomorrow then?
What's my day like tomorrow? Well, we have the most favorite time of the month tomorrow at lunchtime, which is called faculty meeting. Sometimes we refer to it as death by faculty meeting. But so it's indeterminate how long that will last. So I might have time in the morning. But if you want to come and visit me outside office hours, I'd appreciate an email just to let me know that you want to come. Not because I don't want you to just drop in on me, but because sometimes I've got meetings planned with students and you might be hanging out there for an hour or two. So there's a lot of things that I have to juggle. Like I said, I want to help, but let me help you maximize your time and my time. So just shoot me an email, tell me you want to come, and I will. If I've got some open slots, I will certainly carve out a slot. And you can just send me an email and ask me, do you have an open slot right now? Well, sure. Okay. So, yeah, somehow Tony's emails end up in my junk mail. I don't know why that is. Okay, anybody have any questions they want to ask? 2 bits, joke of the day? Did I tell you the one that my 3-year-old told me? She has these bunch of jokes she likes to ask. She says to me, so, I've got a funny joke. Okay. What's the difference between a rock and a car? No, that's the joke. There isn't an answer. And then she just laughs hysterically. She thinks that's hilarious. Anyway, so you were half maybe thinking about raising the hand.
On question 3, we're supposed to derive that equation.
Question 3, we're supposed to derive the equation, yeah.
What's that really supposed to describe? Are we supposed to measure the time it takes to print out the difference between characters, floats, and ints, or?
Okay, so a reasonable equation is just okay. So what I want you to do is with that is apply your noggin and figure out what is a good equation that models the performance of printf. Is there any difference between printing out ints and floats? And if so, can you come up with one equation that says, okay, here is a buffer. If you're modeling this buffer that's a sequence of characters and you print it out, does that, if it's a sequence of, or if you were printing out an array of integers, well, it just gets kind of messy on how would you really account for that. For the most part, the most basic fundamental equation I'm looking for is, given a string of characters that you don't do any format conversion on, how long does it take to print that out? And then I want you to account for how long does it take to do format conversion. Okay? So what you should do is think about what are the processes involved in doing this in printing. And digging through all the source code, you're going to find, number 1, there is transfer from the serial port. Number 2, there's all that junk that printf does. What is the junk that printf does? Well, the most simple way of traversing through that code is give it something that it doesn't really have to do anything with. You just give it a block of characters that it doesn't have to do any format conversion. And then just see how long, what's the overhead on just printing out this sequence of characters where it doesn't really have to do anything, but it has to call all those functions in between here and there just to realize, oh, I don't have to do anything. What's the overhead for that? And then, after that, what's the overhead if you did have to do format conversion? Okay? So those are the three separate things you've got to kind of account for and figure out how long does each of these phases take. And if there's no difference between format conversion for an int, a double, and a char, then you can have just one equation. But it's okay with me if you just have a simple equation that just says, if it turns out that those three things aren't different, then you just have one equation that says, what's the cost on a per character basis to do the transfer? Okay. Another way of doing this is saying what's the average cost over different types of format conversion for the data transfer on a per character basis. Okay. So use your noggin and kind of tell me what you think is an appropriate equation for modeling the performance of printf. Given that level of leeway, I am going to tell you this much. If you have a thorough analysis and you provide me a half-decent answer, even if it matches what nobody else says, I'm going to give you credit. Okay? What I'm looking for is that you used your head and figured out how do I model performance of printf, and you gave me something that's reasonable. And so there's plenty of right answers. I'm sure there's a whole slew of wrong answers, but there's plenty of right answers. I'm more concerned about process than result on that one. Okay?
So that's time from the board, or is this just a general printf function?
So this is how printf executes on the TS7200 board, given the tools and runtime system that I've supplied you.
So we just modify the .c file and create our own file, load onto the board.
You can do so. The question is, do you modify the p.c file or make your own file? I don't care. I would suggest hacking p.c because you've already got a make file set up to build it. Or use a stopwatch. You could, if you really, really want to, you can do this without having to write code. You wouldn't be doing a very thorough job, but you don't have to write code for this problem. I would suggest that you do write some code because it makes your life much easier. You can you can hack both the target side and the host side loader, the target side program and the host side loader, and you do the host side loader automate the timing stuff, and the target side to send out some characters. I'm starting to print now, and you print out different amounts of data and measure how long it takes and calculate averages and all that. I kind of like to let programs do my work for me. Steve?
Is there a certain way you want us to, like when we're explaining what like printf function does, is there a certain way you want us to show that? Like go, say this function calls this function calls this function?
Okay, so the question is there a particular syntax of specifying what printf does that I'm looking for? Not necessarily. I don't want to impose on you guys a particular syntax, because digging through printf hard enough, and then trying to figure out what in the world is he saying by you want a call graph, and how do you model a call graph, and you want it HTML and linkable and all this stuff. No, just make sure that I understand, that you understand what it's doing. Okay? So it can be graphical, it can be textual, I don't care really what it does. If I were doing this, I'd pull out Visio and draw a flow graph. And then I'd have an indexed description, because I'm requiring you that you give a 1 to 2 sentence description of each function, just so I know that you know what each function is supposed to do. But you have to have that description for each one of the functions, and then I just put a flow graph. But that's me. You don't have to draw anything. You can just use text if you want to. Okay? Mitch?
I don't know if you already talked about this, but wondering if you could explain, again, you already explained to me once, what exactly is reentrancy,
Okay.
and how we achieve that with that global reentrancy.
Okay, so the question is if we could just talk briefly about what is reentrancy and what is this reent data structure that's in printf. Okay, we are going to beat this sucker to death, but we're not ready to do it yet. Not necessarily the reent data structure, and I'll explain a little bit so that you can have enough information about it for understanding what's going on with your labs. But we're going to talk much more in depth in the context of the operating system we're building about reentrancy. So more on this later, but specifically for this lab, when you're thinking about reentrancy, what you're thinking about is multiple threads of execution simultaneously running the same block of code. Okay? So let's suppose you had two threads. Now, threads share address space, they share data, and they can share code. What if you had two threads running and both of them called printf? Well, they're not calling printf at the same time because you've got a single processor and it's only able to run one thread at a time. So one thread went through and started calling printf and got into the middle of the printf code, and then it got preempted and swapped out. And then another thread got swapped in and started running, and let's suppose it called printf. And so they're both executing the printf code. Is there some artifact of the fact that you've got two threads executing the same amount of code that's going to mess something up? Okay? I'm not going to tell you exactly what the messing up is because we need more concurrency theory in order to talk about that. And we'll talk about that when we get to Chapter 7. But the issue is that when two threads access a certain block of code, if accessing that block of code causes data structures to be shared between them, if those two threads access those that shared data structure in the wrong way, it could cause the printf to get messed up. So it could cause one thread's printf to get mixed up or get overwritten by the other thread's printf. So what that would happen is you'd see a portion of one thread's print, and then you'd see the other thread's print, and maybe a portion of the first thread's print would just get overwritten. So we're trying to keep the printfs from getting messed up. Not being messed up would be you see a portion of the first thread's print, then a portion of the second thread's print, then the rest of the first thread's print. If all of the thread's data that both of them are trying to print end up on the screen, that's correct behavior. It might not look pretty, but that's correct behavior. Incorrect behavior is where you lose data that should have been printed to the screen, but it just gets dumped. And that could be just by the artifact of you've got these two threads both accessing data structures that they are implicitly sharing that weren't necessarily intended to be shared between threads. Reentrancy. The goal of designing a reentrant routine is a routine that will not mess up or will be resilient to having multiple threads executed at the same time. Or in other words, those critical sections inside the thread are protected. So how that is embodied in the C runtime library is we try to collect all these data structures that are shared. Anything that holds global state, we collect that into a single data structure labeled reent. Okay? So all that state information is packed into that one data structure. So that's where you're defining stuff that multiple threads would share. So that's basically why we have this reentrancy data structures. Every time you get into printf, it says, well, I'm going to pass along the stuff that's inside the reent data structure. That way every thread that accesses printf, all of them explicitly access that same reentrancy data structure. Now, if we were explicitly handling reentrancy, we would have to protect the access to that data structure with semaphores. And again, we'll talk about how you use semaphores to protect shared data structures later on, so you don't need to worry so much about that. But all this is one spot that has all the information that anybody who's using printf would use. It's kind of like a pointer to a big structure that has a whole bunch of variables that would otherwise be global. But they're all stuck in this one data structure. So everybody who calls printf references that one single data structure. Everybody within the program that you're running. Different processes have their own data structure. I know that doesn't make a whole lot of sense, but it's just, you just think about it as one single repository that's got everything that you need that's global. And it's so that you can protect it if you need to when you're doing calls to printf from multiple threads. Okay? I won't ask if that makes sense, because I don't think it should at this point, but hopefully that gives you enough information to understand what is this reent structure for. Other questions? Have you looked at checkinit yet? Have you looked at checkinit yet? Checkinit. Checkinit is a macro. You got to check it. Okay. All right. Again, I would be happy to help you with this. I'm a pushover when you come to my office. I give away all the answers. Okay. Parameter passing. So we're going to finish off programming in the small today. And then I was going to barrel on into Chapter 4, but I think we're going to instead start talking about Lab 3 and go into nuts and bolts as soon as we're done. And it's good stuff, because let's start talking about interrupts. Okay, parameter passing. This is just a review of the C calling convention. How are parameters, when you call a function, how are they passed to the function you call? You pass them on the stack. So if you've got some function called fn that takes two parameters, a and b, and you've got main here that calls a and b, passing it the values 3 and 10. What happens in assembly is something that looks kind of like this, where you push 10, then you push 3, then you push the return label, and then you jump to underscore fn. Okay? The return label is down here below the jump. So you got this return label colon, and then the first thing that you do after you're done is you pop, and then you pop. What am I popping? Well, I'm popping these guys. Okay, I'm popping the parameters I pushed onto the stack. Okay, what does this do? This is the C calling convention. This is a convention that's applied in assembly language when a function gets called. When you're calling a function, it's the caller's responsibility to put the parameters on the stack. And you put the parameters on the stack in the order of right to left. Right to left as dictated by the order they appear in the function's prototype. So I'll push on the value for B, then I'll push on the value for A. Then the caller pushes the return address onto the stack, and then it does an unconditional jump to the function that you're calling. Okay? Then that function does its thing, does whatever computation it's going to do. It leaves these values, these parameter values, on the stack. It will reference them and copy them off and do things with them, but it will not adjust the stack pointer to remove them. Okay? The caller, one thing that it does do is it will remove the return address from the stack, and it'll jump to it. Why will it remove the return address? Well, because the only consumer of this return address is the called function. So that called function will grab the return address, which tells it where do I need to go back to, which is this address of the next instruction following the call to the function. So the callee will pop the return address from the stack and jump to it. Then the C calling convention dictates that it is the caller's responsibility to clean up, or in other words, to remove the parameters that were pushed onto the stack from the stack. Okay? So this is an example of the C calling convention. You push parameters right to left, you push the return address, you jump, then the callee will pop the return address and jump back, then the caller cleans up the stack. Okay. Different architectures do this a little bit differently. x86 does something that looks very much like this. On the ARM processor, we do something that looks similar to this. But instead of using the stack for passing parameters, if you have 4 parameters or less, you pass them in registers. Okay? And then you also pass the return address in a register. Maybe some of you have seen the BL instruction inside the file that's got the entry point to the C program. Okay, that BL instruction means branch and link. What that BL function does is it does these two guys all in one, the push ret label and the jump fn. Branch and link. Link is a term that means save the return address. On an architecture that's stack-based, you would then push that return address onto the stack. But because we're not stack-based on the ARM, we do have a stack, but we try not to use it. So what we designate is one of our 15 registers that we have, one of our 16 general-purpose registers, we designate as a link register. So what that link register is used for is for holding the return address when you jump to a subroutine. So the BL instruction on the ARM will say, give me the return address, put that in the link register, and then do a jump to the label of where I'm trying to go to. So on ARM, this would be like copy 10 into one of the registers, copy 3 into another one of the registers, BL underscore FN. Okay? So that way we're not pushing and popping unnecessarily. The return instruction on the ARM, the equivalent of the return instruction, what it does is it will copy the contents out of the link register and jump to it. They're guys that I had in class last year. So the ARM uses registers for passing this. So it's still the C calling convention. You still dictate the order in which you use those registers in right to left, and you use the register for passing the link. But you need to keep in mind this is the C calling convention, and the ARM does this, but using registers instead of the stack where it can. If you've got more parameters than you have available registers for doing parameter passing, it will use the stack. Okay. The other thing to remember is that when you pass parameters to a function, you pass copies of those parameters. You don't pass the parameter itself. Mitch.
So, when you say if we're using the stack, if there's more than 4 parameters, you mean the compiler?
The compiler will insert, so if it's got more parameters, what that means is the compiler will recognize that I need to pass more parameters than I have parameter passing registers. And so the compiler will insert instructions to push those guys onto the stack. Yeah, the compiler does that analysis, which is why it needs to know a function prototype when it's going to call a function. So it needs to know how many parameters you're passing. Okay. You can only pass copies of stuff. So you don't pass the 10 that you created in main. You pass a copy of the value 10 you created in main. That might sound silly, but we don't have pass by reference. And pass by reference does not exist literally in assembly. You can implement pass by reference by hiding the details of passing a pointer to an argument and dereferencing it, but you have to pass copies of things. Okay, so if you want to write to one of the variables that you pass as a parameter, what you have to do is you have to pass a pointer to the variable that you want the function to write to. And that function can access the variable that you want it to write to by accessing its address. So you can pass a pointer, and then the called function can access that variable by dereferencing the passed pointer. But the thing to note is the pointer gets passed by value. So you can either pass a value by value, or you can pass a pointer by value, but you're always passing by value. Okay? So as an example, here is the function calcsum and a function main. So let's suppose we've got a function calcsum that just calculates the sum of A and B, and it takes a pointer called res, and what it'll do is it'll take the sum of A and B and it'll write to the memory location pointed to by res the sum of the contents of A and B. So int 1, int 2, int res, so int star P equals the address of res. So what I'm going to do is I'm going to call calcsum. I'm pass it the variable 1, the variable 2, and the variable P. So calling this function, I would pass a copy of P, a copy of 2, a copy of 1 onto the stack. Pushing a copy of P passes not the variable res. It does not pass the variable address of res. It passes a copy of the address of res onto the stack. So calcsum does this, where I say star R equals the sum of A plus B. So I'm dereferencing variable R. So a copy of an address is just as good as the address itself. At this point, you've got this pointer R that points at the variable res, and you've also got the pointer P, which is declared up in main, as a pointer to this memory location. You could access P. Let's suppose that both P and R were in scope at the same time. You could use P to access res. You could use R to access res. Even though they're different pointer variables, they both point to the same memory location. There's no difference between using P or R to access res, except for the name of the variable you use to access it. So passing pointers and passing copies of pointers works just as well as passing pointers. So C only supports pass by value. C++ has pass by reference. But again, this is a compiler trick. What happens at the assembly level is it will pass a copy of a pointer to a variable that you are passing by reference. And then when you access that variable that is passed by reference, it will dereference the pointer at the assembly level. So the pass by reference is implemented as passing by pointer by value. Okay? So just because C++ has pass by reference, there's nothing magical going on at the assembly level. All that's going on under the hood is you pass an address and dereference the address as you under the hood. Okay? So, now, pointers to functions. A function is a label, right? So you've got main, we talked about underscore main, colon, and then all the assembly instructions that follow it. Well, a pointer, or a function here, you can think about that on the assembly level as a label. What's a label? It's an alias for an address. What's the address? It's the address in memory of where I'm putting the first instruction of that function. Okay? Well, can we deal with that concept directly and explicitly in C? we want to be able to define a variable which contains the address of an instruction. This is how we do it. Okay? So void here, this is the return type of a function. Here's a list of parameters of a function. fnptr, what this is a declaration of a pointer variable that instead of pointing to a particular type of integer or char or float, this guy is a pointer to a function. What does a pointer to a function mean? Well, it's actually a pointer to an instruction, the first instruction of a function. fnptr is the name of the variable. The syntax parent with a star in the middle here right next to fn pointer, that indicates this is a pointer to a function. The other stuff surrounding it gives the return type of the function and the list of parameters I'm passing to the function. Okay? So this is funky syntax, but this is how you declare a pointer to a function. This just declares the pointer. It doesn't point it to anything. How do I point it to something? Okay? Let's suppose I have this function prototype here, void fn1, int t1, int t2. This says there is a function defined somewhere, named fn1, that takes two parameters that are both ints and returns a void. This function is type compatible with that function pointer that we declared because that function pointer we declared took as parameters two ints and returned a void. This takes as parameters two ints and returns a void. It doesn't matter that t1 is not named the same as a. All I care about is the type, not the name of the parameter that I'm passing. I just care about the type. fn2 is not type compatible with that function pointer because it returns void, which is fine, and it only takes a single int. Okay? So how do I assign the function pointer? Well, if you want to assign something, I would suggest the assignment operator. Pretty straightforward. Fn pointer equals fn1. If you try to do this, fn pointer equals fn2, your compiler is going to yell at you. In the same way that it yells at you if you take a char and assign a double to it. It's going to say, I don't know that you know what you're doing. Are you sure you really think you know what you're doing? And then you start to scratch your head and think twice. And then you proceed to turn off all the warnings and say, yeah, I know what I'm doing. Please don't tell me anything. And then your program crashes. But this right here will give you a type error because you are trying to assign a function pointer the value of the address of a function, and it's not type compatible. Yeah.
Does that function pointer point to the beginning address of the function?
Does the function pointer point to the beginning address of the function?
Right.
Okay,
So
it contains the address of the first instruction that gets executed when you jump to that function.
Okay.
So in the same sense of at assembly, when you say jump underscore fn, that underscore fn is a label, and that represents the address of the first instruction.
Okay.
That's the address. That's the value that this variable fnptr would contain. So instructions have addresses, just like variables have addresses. Okay? If I want to have a pointer variable that contains the address of an instruction, I use a function pointer. Okay? It just so happens that the C syntax supports you taking the address not of any generic assembly instruction, just those instructions which happen to have a label or those instructions which happen to come as a function. Now you can pull the pants down on that and just use an absolute address. In fact, you already have this semester of using an absolute address, casting that to be a function pointer and jumping to it. Where have you done that? In the bootloader. So what I had in there was a type def that defined the type of a function, the type of a function pointer. So right here. So this was in lab 1, or this is in bootloader, void star fn void. So I tacked a type def on the front of that. Okay, so what this does, this type def is kind of funky. Normally with a type def, what you're doing is establishing an alias from one kind of type to another kind of type. A pre-existing, already defined type to a new type. This looks like I've just got one statement here, or somehow I'm defining void as fn void or something like that. But really how you interpret this is I'm defining fn as a type. Not a variable, a type. So this is like type def Fred int, or int Fred, something like that, okay? This is now going to be a type name. What is the type of, what's the old type that I'm defining this new type to be? The parent star void void says fn is type def to be a pointer to a function, and that function takes no parameters and returns nothing. Okay? So this is defining a new type called fn, and it's a function pointer type. It's different than when I defined fnptr. When I defined fnptr, I declared a variable. This does not declare a variable. This defines a type. If I wanted to define a variable of that type, I'd say fn space var. Then var would be of type function pointer to a function that takes void and returns nothing. Now there was this statement inside lab 1, inside the bootloader, where I took 0xabcd. It wasn't actually 0xabcd. It was, well, anyway, this statement exactly didn't appear like that in bootloader. But you can take an absolute address, 0xabcd. I can put it in parentheses. I can cast it to be of type fn. Okay? So what that does is it says, assume that number is an address, cast it to be of type a function pointer that takes no parameters and returns void, and then putting that in parentheses, and then having those parentheses outside it, that just does an absolute jump. That will compile down to, in x86, jump 0xabcd. Okay? So this is one way to really disable all the mechanisms that you keep yourself from shooting yourself in the foot. You better really know what you're doing if you're trying to do this. But this is under the rare circumstance where you know what address you need to jump to, and this is how you implement an absolute jump in C. Yeah, it'd be a call. Be a BL in ARM. Okay. Questions on that? So now you know how to jump to bad beef if I tell you jump to bad beef. If I tell you jump to bad beef, you say how high? All right. Will I or will I not? Why would I want to do that? Yes?
So, with a function pointer, we're not actually not calling the function, so we're not worried about passing pointers. Is that how it,
So this guy is calling the function. This says assume that at address 0xabcd there is a function, and it's of this type. Cast it to be a function pointer and then call it. I never showed a call to fnptr in this. In order to show a call to fnptr, it'd look something along the lines of, so after here, what I could say is fnptr 1, 2. And depending on the syntax, you may or may not need the parentheses here. Different compilers interpret things a little bit differently, and sometimes you need to insert random address or random ampersands and stars when you're doing the assignment here to get it to work right. But just some compilers are persnickety. Yeah.
So if you were returning something, could you say like x is equal to fn?
Yep. If you were returning something, then you would have some variable x and set it equal to x. You'd set it equal to that thing, and that would take the return value and put it into x.
Maybe you've already answered this, but I didn't understand it. Why would you want to do that? Why would you want a function pointer?
Why would I want to do this in the first place is a good question. Okay. So the question is, why would you want to do this in the first place? Why support this feature? And the reason is, well, take, for example, the bootloader code. You know, if you didn't have the ability to have function pointers, you wouldn't be able to write a bootloader in C. The reason why C supports it is because you can do it in assembly. C is designed to be a high-level language that mimics assembly code. Okay? Where more often you find something like this is, say, for example, you were writing a, let me see if I can cook this one up without confusing all of y'all. Let's suppose you were writing a utility that, or a program that receives data from some source. Let's suppose you didn't know what that data source was. Let's suppose that if you got an int from that data source, you wanted to call this function. And if you got a var, or if you got a char from that source, you wanted to call this function. Well, you could do a runtime, and let's suppose that part of the data that you get says, here's the bytes that I'm sending you, and here's a flag that says, what is the byte? And then you could use a switch statement, and inside that switch statement, you could go and invoke each of the individual functions just with a regular old function call that dispatches the call. Okay? Well, let's suppose that let's suppose that instead of writing that switch statement, you wanted to do things a little bit more efficiently, and you wanted to define a lookup table where you said, okay, I've got all these different functions that I could call. So instead of doing a switch statement on here, you could just have an index into an array of function pointers to say, okay, I got this flag indicating I got an int. Let me drop that in to look up the function that I'm supposed to access. And I'll access that function pointer, just jump to it. So it avoids the switch statement completely. So there are reasons why you need to do this. It's the same reason of why would you ever want to have a pointer to a data variable in a context other than I want to pass it by quote-unquote reference. So it's convenient to have a level of indirection at times. And if you end up being a C programmer in your career, you'll use function pointers eventually. And then after you do, and you go and you look at the C# or Java, you will curse the fact that you can't use function pointers in other languages. Okay. Now, signed versus unsigned. So here I'm just giving away all the little tips and tricks that make C programming mystical to some people, but will make you guys masters of the C programming language during your careers. This is one way that gets people into trouble. I show this when I teach 3720. Not in exactly this format, but similar. Okay, so signed versus unsigned. What's the difference between a signed number and an unsigned number? So they are both. So let's talk about a signed int and an unsigned int on a 32-bit Linux machine that has a word size of 32 bits. Okay. So your unsigned int and your signed int are both 4 bytes. Can you represent one using a signed int? The number 1. What does it look like? In binary. Bunch of zeros followed by a 1. How about as an is there any difference between the signed int representation and the unsigned int representation of the number 1? How about the number 10? Any difference? How about the number 65535? Any difference? No difference. How about the number -1? So you can't represent a negative number in an unsigned integer. Well, what's the bit representation of -1? 1, 1, 1, 1, 1, 1, 1. Everything's a 1. Well, okay. Are you telling me that I can't put a whole bunch of 1s into 4 bytes and call it an unsigned integer? But you just told me that I couldn't. Wait, so can I or can I not fill 4 bytes with 1s as a signed integer? Can I or can I not fill a byte full of 1s as an unsigned integer? So why can't I show -1 as an unsigned integer then? Because all 1s mean something different when you're thinking unsigned int as compared to when you're thinking signed int. Okay. When you convert between signed and unsigned, there is no conversion that happens at the bit level. All that happens is how you interpret the bits. Okay? So, let's look at a few examples. Let's suppose I've got a variable char c equals 0f, and I say printf %d, comma c. What does that print? Prints 15. Okay? How about unsigned int d equals c, and I printf %d? 15. Okay? Char c equals 0xff, printf %d, comma c. Printf, that gives me -1. Okay. Did you see it? Okay. How about if you print unsigned char d equals c, and then you printf %d, comma d? What's that going to print? -1? What does %d say? Decimal, signed or unsigned? Signed. Okay. If it were unsigned, why would on this upper one I get a negative number? So I'm going to take unsigned char d equals c. So then I say d is, so this conversion doesn't change anything. So what does D contain at the bit level? All ones. So what happens here? I say printf %D, comma D. Get 255. Why do I get 255? I've got all ones. Why am I not interpreting all ones as a -1? This thing says I just printed all ones as a %D, I got -1. At the bit level, this guy has the exact same thing as that guy, and yet I say printf %D and I get 255, not -1. What gives here? Who's cast? Well, I just told you casting it doesn't change any bit level representation. Printf is not doing something. What does %D say? What does it really say? Take what off of your argument list and convert it into a base 10 integer? How many bytes? 4 bytes. How many bytes am I passing? What's the size of an unsigned char? So what happens here? It's going to expect 4 bytes, but I'm passing 1 byte. So when this happens, your compiler is going to insert code to say, I need to convert this to a 4-byte number. And so you're going to push 4 bytes onto here. So it will grab that 1-byte number and make a 4-byte number out of it. Is the 4-byte number going to be signed or unsigned?
Or signed.
It'll be unsigned because of the fact that I start with an unsigned.
Yeah,
So I'm not going to sign extend this guy to a 4-byte number. So I will take 1 byte of all ones, tack on 3 bytes of zeros, and pass that. Which, when you say %D, 0, 0, 0, 3 zeros plus FF ends up with 255. Okay. How about this one? Now that we're sufficiently confused, int I equals C. I'm going to printf %D, comma I. So remember, C over here was initialized to FF, and I just say I'm going to declare an int I equals C. What this does is it says copy that value over here. But because of the fact that this is doing a sign-to-sign conversion, I'm going to sign extend this guy to a 4-byte number and copy it into that 4 bytes. So that way, this I consists of 4 bytes of 1 instead of 1 byte of 1. So that's why I get -1. Now, if I say unsigned int UI equals C, what goes on here? Well, the type conversion doesn't change or toggle any bits. But what I'm going to do, if I say %D, comma UI, I end up printing 255. The reason why is the same thing has happened up there. I take this guy, I convert it to a 4-byte number, and I copy it over. When I do the conversion, I'm not changing it to a signed number. I don't do the sign propagation. So this ends up being 0, 0, 0, 0xFF. Okay? And that way I pass 0, 0, 0 FF to that guy, and I end up with 255. Interpret it as a base 10 number. Okay, so this is the explanation of what I was just talking about. I ends up with all F's, UI ends up with all zeros except for the last guy. This did not get sign extended, this did get sign extended. Okay. Now, so this guy unsigned it, UI2 equals C. And then I printf %D UI2. I print an unsigned integer, and I get a negative number right there. Wait a minute, I just printed an unsigned integer using %D, and I got a negative number. I thought you just told me you couldn't represent a negative number using an unsigned int. How many of y'all want to curse now? I should make you trace why this happens in the printf source code. Okay. So what happens here? %D says, take whatever you're given and interpret it as a signed integer. UI2 contains all F's. Why did we sign extend? What we do is we have to convert from a 1-byte number to a 4-byte number. You take the source value, you make the source the same width as the destination, And in order to do that, we sign extended the source, and then we copied it over to the destination. So we took a 1 byte signed integer, made a 4 byte signed integer out of it, and then we did the cast to be an unsigned integer. And that cast didn't change the underlying bit representation, so I passed 4 FFs to printf. And printf says, take the first 4 bytes and interpret that as a signed integer. So because I passed all f's, it printed -1.
They always look at them as.
Okay, printf looks at the percent code that you pass it.
Right.
And it doesn't look at the data type of the value you pass to it, because all you're doing is passing bytes.
Okay.
So it just takes the content of the variable, copies that onto the stack. It doesn't know that you were holding that in an int or an unsigned int or a char or whatever. It just takes those bytes and interprets them how you told it to interpret them.
So when you're assigning a variable to the value of some other variable that's of a different width, it makes the width match first.
So if you're doing an assignment from dissimilar types, what it'll do, so if they're compatible but dissimilar widths, so like a char to an int or whatever, what it'll do is it'll first take the smaller guy, make him of width the size of the bigger guy, and then do the assignment. Casting if necessary. Yeah.
What was the difference? Before we got 255, we assigned UI is equal to I, is that how, or whatever?
Okay. So over here we said unsigned char D equals C. Where's this guy? Is that the one you're talking about?
This when you started working with images.
Okay. This guy. Unsigned int UI equals C. So I take an unsigned int UI equals C, and I print at %D UI, and I got 255. And I say unsigned int UI2 equals C, and I present that, and I got -1. You know what? Those two contradict each other. Interesting. I'll have to look that one up. Because I ran all those guys on GCC, but I ran them last year, so I'll have to make sure that those... Anyway. The rule of thumb still holds, even though I contradicted myself. Use signed integers, unless you really, really know what you're doing. Don't use an unsigned integer unless you're trying to represent something in hardware, or unless you absolutely have to have the extra bit of precision. Okay, use %u to print up a number as an unsigned number. Just because you have a loop counter that goes for I equals 0 up to some number, don't use an unsigned integer for a loop counter variable. Use signed integers unless you need to use an unsigned. Okay, the other thing right here, when you take size and 0x80, what this says is I've got 0x80, which is a constant, and I've got a size. Let's suppose that it's a 1 byte number. What this happens here, a constant is represented as a 4 byte number. Okay, so because I'm going to do a 4 byte number, bitwise AND with a 1 byte number, it's going to take this number and convert it into being a 4 byte number. So if this is a signed number, then what will happen is it'll sign extend the number and then do the operation. If it's an unsigned number, it'll 0 extend the number and then it'll do the operation. So if any bit in the 4 byte result is non-zero, then this produces true. Okay, so you got to think about what are the impacts of what you're doing on the size of the variables you're operating on. Okay, the other thing that we want to point out is relational operators. Okay. Negative, if you put this into an if statement, if -1 less than 0, that should always be true, right? Now if I put -1 less than 0u, that u is how I say, so all constants you specify in your C program are interpreted as 4 byte signed integers on a 32-bit machine. Okay? If I want to interpret the constant as an unsigned integer, I tack a u onto the end of it. So I just say 0u, and that means this is an unsigned integer. If I put if -1 less than 0u, that'll evaluate to false. Okay? This one evaluates to true. This one evaluates to false. Why does this evaluate to false? Well, because what happens is relational operators will look, if I'm mixing signed and unsigned, it'll pick the unsigned interpretation of the bytes that I'm comparing. then I would interpret -1 as an unsigned number. -1 as an unsigned number is all S, which is a very large a very large positive number. A very large positive number is not less than 0, and so consequently -1 is indeed less than 0 unsigned. So that evaluates the false. Okay? All right, so next time we'll mention alignment, then talk about interrupts. What does that do? What is a char? A char is an 8-bit signed integer. It just happens to be named char, and so when you're naming something char, you start to think it's a character. It's not a character, it just happens to be named char, and that can be used as for holding character data.